All right, we're in section 8.2, where we want to look at the graphs of the other four trigonometric functions: tangent, cotangent, secant, and cosecant. So in 8.1, we spent a lot of time looking specifically at the graphs of sine and cosine, and then transformed versions of those graphs that we call, of those functions, we call them sinusoidal functions. And the techniques that we developed in 8.1 for graphing those, in large part, do carry over to what we do in the graphs of the other four trigonometric functions. They're not exactly the same. That you'll notice that the graphs actually look quite different than the sine waves and the cosine waves that we saw in the previous section, but it's the techniques themselves that seem very familiar. So we'll kind of get to that in a minute. Also, don't mind my dog barking in the background. That's just kind of part of working from home. So I want to start by looking at the tangent function. And in order to graph the tangent function, we're going to do something similar to what we did initially in 8.1, which is create a table. But we need to be a little bit more cognizant of what's going on with the tangent function than just plugging in the values in that table, because there's a lot of behavior of the tangent function that's not apparent by just looking at some of those familiar unit circle values. So in order to get a good sense of this, let's talk about that trig identity: tangent equals sine over cosine. Okay, the fact that tangent of x is equal to a quotient like this means that there's going to be values where the tangent function is undefined. We already know that to be true. We talked about that in chapter 7. And specifically, if cosine of x, for some value of x, if cosine of x is ever equal to 0, then tangent of x will be undefined there, because then this is dividing by 0. So we know that the graph of our tangent function shouldn't have any part of the curve that we sketch passing having a value where cosine would be equal to 0. But it's worth looking at what happens when x is close to those values. So let me get a little bit more specific here. When is cosine of x equal to 0? Take a look at the unit circle for a second. Here's the unit circle. Remember, cosine of x is equal to 0 at the points on the unit circle where the x coordinate is equal to 0. That would be here or here. Cosine of pi over 2 is equal to 0. And cosine of 3 pi over 2 is equal to 0. And those aren't the only two values, because remember, we can start at a point on the unit circle and take any number of revolutions to get angles that are coterminal to pi over 2 or 3 pi over 2, and cosine of those angles will still be equal to 0. So those would be angles like negative 5 pi over 2, negative 3 pi over 2, negative pi over 2. Notice negative pi over 2 is coterminal to 3 pi over 2, so that's still talking about this point here. Pi over 2, 3 pi over 2, 5 pi over 2, any number of those, produces a cosine of 0, and tangent will be undefined at those values, right? Symbolically, we can write that this way: x equals pi over 2 plus pi k, where k is just any integer. Now think about this for a second. Pi over 2 represents this angle up here, right? It represents the like a 90-degree angle from the positive x-axis. That's right here. What is this plus pi k talking about? Well, if k is an integer, let's just let k equal 1 for a second. If I do pi over 2 plus pi, on the unit circle, that's like starting at pi over 2, adding pi, which is half a rotation around the unit circle, and taking me down here, where we also know tangent will be undefined. If I make k equal to 2, pi over 2 plus 2 pi, that's 2 half rotations. So that, again, that's like starting at pi over 2, adding a half rotation, adding another half rotation. If k is a negative number, say negative 4, then that's like starting at pi over 2 and making 4 clockwise half rotations. 1, 2, 3, 4. And you can see that any number of half rotations in either direction just takes me back and forth between these 2 points where tangent is undefined. So that's what this is talking about. When x is equal to any of these values, and because k can be any integer, this is an infinite number of values, tangent will be undefined. We didn't have that problem with the sine and cosine graphs because those functions are defined for all real numbers. They're never undefined anywhere. So we didn't have to think about what happens to a graph when a function is undefined. And we'll talk about that shortly. In order to get a sense of what's happening at these values, where tangent is undefined, since we can't plug pi over 2 into the tangent function, let's plug in numbers that are very, very close to it and just think about the behavior of the tangent function near those values. For the purpose of plugging things into a calculator to check this, it's easier to work in degrees in this example. So we're going to temporarily switch over to degrees. Pi over 2, where tangent is undefined, is the same thing as 90 degrees. So tangent of 90 degrees is undefined. But what if you look at values that are very, very close to 90 degrees and plug those into your tangent function? What's happening? Tangent of 89 degrees. 89 is very close to 90 while still remaining less than 90. Plug that into a calculator and we get a value that's approximately 57.29. What about if I plug in 89.9 degrees? That's even closer to 90 degrees. Now I get a bigger number, 572.96 approximately. What if I get even closer to 90 degrees, 89.99 degrees? That's very, very close to 90 degrees. Plug that into my tangent function and I get a significantly larger number, 5,729.58. In fact, it looks like these numbers are increasing by a factor of 10 every time. This is roughly 10 times this is roughly 10 times this. That's not quite as important as the observation that this number is seeming to get larger and larger without really stopping. And that's what's actually going to happen as this angle in here that we're plugging into our tangent function gets closer and closer to 90 degrees, which again on the unit circle is like making angles that are approaching this point but never quite getting there, just getting closer and closer and closer. The tangent function is just skyrocketing to infinity. So we have to think about what that does to our graph. Similar down here, if I plug in values that are near 90 degrees but slightly larger, like 91 or 90.1 or 90.01, you're seeing similar behavior happening to what we saw up here, except these numbers are negative. Now, why is that happening? Well, again, 90, 90.1, 90.01, all of those angles in degrees would be in the second quadrant. Those are all here. Again, they're getting very, very close to that point up here, that 90-degree angle, but never quite reaching it. Tangent, we know, is always negative in the second quadrant, which accounts for why these are being negative. But in spite of that, as we get closer and closer to 90, this value that we're getting out of our tangent function is plummeting downward towards negative infinity without seeming to stop. In math, we call that asymptotic behavior, meaning as x approaches some particular value, the value f of x, in this case tangent of x, is shooting off towards infinity or negative infinity without ever stopping. And in the graph of our function, this creates something that we call a vertical asymptote, which we'll see on the next page. Okay, so we want to keep that in mind as we think about the tangent function. Now, let's graph the tangent function. So one important thing to remember about the tangent, cotangent as well, we'll talk about cotangent next, is that tangent is also a periodic function, just like sine and cosine, but it has a shorter period than those functions do. The period of the tangent function is pi instead of 2 pi. And instead of graphing on the interval from 0 to pi, we get actually a nicer picture of the tangent function if we graph on the interval from negative pi over 2 to positive pi over 2. Notice the length of that interval is pi. Negative, or if you do pi over 2 minus negative pi over 2, you get pi. So we're going to use these as our x values. Notice these are x values ranging from the fourth quadrant into the first quadrant. Here's what we get for our tangent function. Remember, at negative pi over 2 and positive pi over 2, we talked about this. Tangent is undefined. Our graph will have vertical asymptotes at these values. But then here's some corresponding y values that we will see. Notice that there's kind of a symmetry here also. So at 0, tangent is equal to 0. That means that the tangent function is going to pass through the origin. That corresponds to the point 0, 0. As we move away from 0 in either direction, do you see a relationship between these pairs of numbers? You should notice that they appear to be opposites of each other. And really what that is it's us visually seeing what we already know about the tangent function, which is that it's an odd function. If I plug in a positive pi over 6, I'll get positive root 3 over 3. But if I plug in the opposite of this input, I should get the opposite of this output. That's what odd functions do. And if you remember, that implies a specific kind of symmetry, which we call symmetry about the origin. We talked about that with the sine function in 8.2. You're going to see the same thing happening in the graph of the tangent function. So if we plot these points, and then remember that these produce what are called asymptotes, we get the graph of our tangent function. Now the part that we would have gotten from the table is actually just this guy here in the middle, okay? And again, you notice for values between negative pi over 2, the negatives didn't print very well, but these are negatives right here. From negative pi over 2 to 0, tangent was negative, putting it below the x-axis. From 0 to pi over 2, from our table on the previous page, tangent was positive, putting us in the positive, or putting us above the x-axis. At negative pi over 2 and positive pi over 2, we had what I was calling vertical asymptotes, and those are denoted by these dashed red lines. What a vertical asymptote does is it represents a barrier that the graph is not allowed to cross. However, the graph will approach it in one direction or the other. So again, remember, as we did this numerical experiment over here, we plugged in values that were smaller than 90 degrees, but getting closer and closer to 90 degrees, and the value of tangent skyrocketed. Graphically, that's what you're seeing happen right here. So again, it says pi over 2, but in degree measure, that would be the same thing as 90 degrees. Our tangent function is getting larger and larger and larger as our inputs approach that pi over 2. So that's why we see this graph approaching that red line, but it's never going to cross it. Because if it did cross it, then there would be a point on this graph with an x-coordinate of pi over 2, which we are not allowed to use in our tangent function. Okay? Now, I also said that the period of the tangent function is pi, and the length of this interval, from negative pi over 2 to positive pi over 2, is in fact pi. So that means that because of that periodic nature of our tangent function, we should expect this graph to repeat itself in intervals of pi, and that's why we have a couple other copies right here. Okay? Now, this shows 3 cycles or 3 periods of the tangent function. When we get to the examples towards the end and we're graphing these ourselves, or actually we'll get to the examples pretty shortly, I'm only going to ask you to graph 1 period like we've been doing with the sine and the cosine graph, because that'll contain all the information that we really need. But before we get to examples, I want to shift over to the cotangent function because it's very closely related to the tangent function, as we know. One relationship between tangent and cotangent is that they are reciprocals of each other. But that relationship is not going to be as helpful in comparing our tangent and cotangent graphs. Instead, what I want to use is the cofunction identity that relates cotangent to tangent, and then I also want to use the fact that tangent is an odd function. We're not going to plug in numbers in a table for the cotangent function like we did for tangent. And the reason for that is because I can actually use the identities I just mentioned and the fact that I know what the tangent graph looks like to more quickly come up with my cotangent graph. So here's how we're going to do that. Using our identities, I know that cotangent of x is equal to tangent of pi over 2 minus x. From chapter 7, we talked about this specific identity. That's the cofunction identity. One of the cofunction identities. There's 6 of them. Now this, going from here to here may seem a little bizarre, but what I'm doing is I'm taking the 2 terms that are inside the parentheses here, and I'm factoring a negative out of them. This is a very common trick in algebra. And what that does, by pulling that negative out, essentially it switches the place of these 2. So my negative x becomes a positive x, and my positive pi over 2 becomes a negative pi over 2 because I pulled the negative out. Now I now have the opposites of what I had here. Then the negative that I pulled out, remembering that tangent is an odd function, can be pulled completely out of the tangent function altogether. That's our odd identity for the tangent that allows us to do that, giving me this. Okay, now what was the point of doing that? Well, remember the goal here is to graph our cotangent function. And if cotangent of x is the same exact thing as negative tangent of x minus pi over 2, I can look at this and think of the negative here and the minus pi over 2 over here as function transformations. What does a negative on the outside of a function do? It reflects it about the x-axis. What does the x minus pi over 2 do? It shifts the graph to the right by pi over 2. So rather than plug in a bunch of numbers and get a graph of cotangent, I'm going to take the tangent graph that I already have, reflect it across the about the x-axis, and then move everything over to the right by pi over 2 units. Now before I show you the graph of the cotangent function, let's think about what that would look like by investigating this graph. If I start by reflecting it, notice that if you look at any one of these little branches of the tangent function, any one of these curves, they are increasing curves, which means as I go from left to right, my graph is traveling uphill. It's getting bigger and bigger, okay? If I were to reflect this blue curve right here, like this, the new curve is going to be decreasing instead of increasing as we go from left to right. So I'm expecting my cotangent function to have decreasing curves instead of increasing curves. Secondly, what's going to happen is if we shift everything over by pi over 2 to the right. Well, notice that if I take this little window here between these two vertical asymptotes, the leftmost asymptote for this particular curve is at negative pi over 2. If I shift that by pi over 2 units, that's going to move that asymptote to the y-axis. And it's going to take this second asymptote right here at pi over 2, add another pi over 2, and take it to pi. So these asymptotes will shift over, and they'll now be appearing at 0 and pi. The other curves will all do similar things. They're all going to flip over, they're all going to shift to the right by pi over 2, and we end up with a graph that looks like this. This one is zoomed out a little bit more than the previous graph, which is why they look more narrow. But these graphs are technically not more narrow than these. It's just a perspective thing. Notice that they are in fact decreasing as we go from left to right, going downhill instead of uphill like our tangent graph. And then also notice that the y-axis is acting as one of my asymptotes, and the next asymptote to the right appears at pi. This would be pi right here, because it's between pi over 2 and 3 pi over 2. Okay? So with that knowledge of the tangent and cotangent graphs, we can now start looking at transformed versions of those graphs. Specifically, if I want to graph functions of the form y equals a tangent of bx minus c plus d, or y equals a cotangent of bx minus c plus d. Now, the effect that the a, b, c, and d have on the tangent and cotangent functions is very much, I shouldn't say the same, but it's very similar to the effects that they have on our sine and cosine functions. For example, b is going to affect the period of these graphs, just like it does for sine and cosine. C and b together are going to affect the phase shift of these graphs, just like it does for sine and cosine. D is going to affect the midline. These graphs have a midline, but we think of it in a slightly different way than the sine and cosine function. In the sine and the cosine function, the way I defined a midline was a line that's oriented exactly halfway between the maximum and minimum values of our sine and cosine function. Looking at your cotangent and your tangent function, we have something different going on here because neither of these functions have maximum or minimum values. You notice the graph here or here, there is no highest point and there is no lowest point because this continues indefinitely upwards and infinitely downwards, so it's never going to stop at some point. However, there is a symmetry to these graphs, and we can kind of see here, either in your cotangent function or your tangent function, that symmetry occurs about this x-axis right here. So you see how we have this intersection about the x-axis, and then this is sort of like a couple of reflections of this. We're going to think of the x-axis in this case as our midline in either one of these. And the effect that D has on that midline is the same effect that it had with our sine and cosine functions. We'll make that more apparent with our graphing examples in a minute. Another thing that's going to change is the fact that tangent and cotangent have different periods than the sine and cosine functions. Remember that if we wanted to find the period of a sinusoidal function, it was 2 pi over the absolute value of b. But that 2 pi in the numerator is only showing up there because sine and cosine have a period of 2 pi. Tangent and cotangent have a period of pi instead of 2 pi. And that changes the numerator when we are looking at graphs for these types of functions. Pi over the absolute value of b instead of 2 pi up there. Last thing that I wanted to mention before we do some examples, taking a look at a. In a sinusoidal function, a, or more specifically the absolute value of a, gave us our amplitude for those functions. Now there is no amplitude for these functions, because remember, the amplitude is the distance between the midline and either a maximum or minimum value. But as we just said, the tangent and cotangent functions don't have maximum or minimum values, so there is no distance that we could call an amplitude for these functions. However, a still does essentially the same thing that it does to a sine or a cosine function, which is it stretches it vertically. That's what causes the change in amplitude for a sinusoidal function in the first place, is a vertical stretch. These guys can be vertically stretched as well. So instead of calling that amplitude, we still use the absolute value of a, but we call it stretch factor. Okay? So we're going to start looking at some examples, and I think time-wise it's going to make sense to start these examples in the next video, so I'm going to stop this one here.